something real quick here, everybody. Okay, so this lab, I'm going to kind of go quickly. I'm just going to show you like a couple of concepts that are important to you need to remember for your regular physics courses. The rest of this lab is going to be kind of like a question answer based on that topic or based on that what I say. Kind of just answering questions about it, kind of like last time. For those of you who are here, I'm going to go ahead and send out an email about this too, but I'm going to give you Wednesday off. I'm a little behind on grading, a couple things. And we have this extra lab, and I want to drop a reminder about that. Okay, so here we go. Newton's second law. Sorry, no, we're doing third law. My bad. Okay, also, I should let you know, the link that I put into section, you're going to want to choose the Google link. You're not going to want to download the PDF. I think the PDF is missing the data. So just use the Google link. Okay. Actually, I should just go ahead and pull it up so y'all can see it really quick. Okay. So this is what you should see. This copy of the lab right here, right? It's lab 6, Newton's third law. Down here, you should see these plots right here. And if you're looking at the version that has this plot, then you are looking at the correct version. Okay. All right, so back to it. Okay. So Newton's third law is the law of the action-reaction pair. Okay, so this generally the statement is for any action, there is an equal and opposite reaction. If you don't like that definition, there's another one that's on the actual lab handout near the top that's kind of cute too. But essentially, this is it. For any action, there's an equal and opposite reaction. So if you have something like two blocks, let's say, and they're being pushed onto each other, like pushed against each other, block A and block B, the force of A be negative the force of B on A. Okay, just to kind of give it some like mathematical underpinning. So, right, that's just kind of a simple concept there, but it's also got some pretty counterintuitive implications. The thing is, in physics, a lot of times, it almost feels like we write these normal forces and these reaction forces just to kind of keep our to communicate to another person what exactly is happening in the problem. So what I mean by that is you can have a table with something resting on the surface, right, some blocks with mass m, and it's going to be pushing down onto the table, right? The table is just standing there on the ground. Okay. The thing is, if we see this, if a physicist sees this picture, we suspect we him to move down. Okay, just to make it as simple as possible. We have some objects sitting on a table like this. This is the table, poorly drawn table. Object sitting there, its weight is pushing it down. If I drew that and showed that to another physicist, then we go, okay, well, we expect this thing to start accelerating downward with a force equaling massive acceleration. So that's acceleration that we would expect. But reality, object on a table, the object resting on table doesn't move down, right? Down in quotations. That's kind of bad handwriting there, isn't it? But okay, so object doesn't object resting on the table won't actually move down, right? So we have to actually have some kind of notation to show that this object is not moving down, right? Right here we would have some force vector pushing it straight down. If there's nothing opposing that vector, then we expect this thing to accelerate straight down. Truth is, there's got to be a force pointing up. Let me come and draw it. Let's draw it like that. That's got to. Right, so this is a force applied, and this is the normal force, and then we're going to see that the force normal should be equal to the force applied in this situation, right? Which is the table resting on the ground. Okay. Now, honestly, it's kind of weird and counterintuitive to think that the table's pushing back up on you, so it can get a little confusing. But essentially, if the table wasn't pushing back up on you, your hand would essentially just, well, go through the table, right? So it's like motion into it, and that's a very basic repulsion of the electrons around your actual atoms that your hands are made of, your hand and the table's made of. It's kind of strange. Also, there's a little bit of Pauli exclusion principle happening there, but it's mostly the electrostatic repulsion, which is why matter doesn't want to collide with other matter. But either way, not to get too philosophical with it, physicists want to be able to tell another physicist, hey, this object is not moving, but gravity is affecting it. Okay. And this is just an example of the action-reaction pair, right? So force of gravity goes down. This FA is gravity. And then Fn is the reaction to gravity. This all here has just been an example. Okay. All right. So that's just Newton's third and hold on. Oh, yeah. Okay, some big ugly fly came in here. Hold on 1 second. Okay, so that's just action-reaction pair, okay? So here we go. So the way this lab's working is actually we have a cart. Essentially what we would do is we would have a single track like so, and we'd have a cart on each side. And they're going to be flying at each other, right? And then they're going to smack into each other. And they're going to apply a force onto each other in the actual collision, right? When they collide, over the duration They're going to apply some force onto each other. These carts have little force measuring instruments on board so they can measure the force. Each cart can measure its force, right? So let's say this is cart A and cart B. So this is like force. This little force here is like, let's say force A, and this little force is force B or something like that. Measure force exerted. During collision. Okay, so that's essentially what we're doing. In the actual lab, we would set these two carts up, we'd throw them at each other. The software we're using would be measuring the force at any given time throughout the entire experiment. They would then measure the force of impact. We would get independent data from the A cart and the B cart to bounce into each other. We would expect to actually be the same for the A and the B cart, right? We expect FA to equal FB, okay, during the collision because of Newton's third law. All right, and that's actually what we will see. The way this is going to be plotted, actually, the data we get is going to look like this. We have force over time. And we're going to have the blue cart, also the A solid will be A, and dashed will be B, okay. What we'll expect is, I'm going to put 0 right here, -5, +5. What we expect is the A cart's forced to be flat until the collision, then it's going to spike to some value, then drop back off to 0, and then keep going. The same thing with the blue force. We would expect it to be 0 until the collision, and then we would expect it to be exactly opposite. There, the best I could. So if we were looking at the force over time, we would see that A would jump up and then come back down, and B would jump down and come back up, just because of the sign difference, right? Because one's pointing to the left, one's pointing to the right, right? So then we're going to have equal and opposite forces, which we'd also expect. Now, this is the plot we would see. We would see that, you know, of course, it would be drawn a little better than the best I could. But that's exactly what we should expect. And that's what you'll see in the data that's given in the lab. You'll see that the acceleration over time graph always kind of look like this too. But the thing that you notice here is that the distance, you know, the height of this, or, you know, this cone here is the force A, let's say, and then the height of this cone here is force B. Okay, they're the same, right? It's the same distance from 0. The very top here and the very bottom here, the same distance from 0. That's what you're going to see, and that's basically that the data confirming for you Newton's third law. You know, it's measuring the force during the collision, and it's saying, hey, guess what? The forces were the equal and opposite, which we would expect. And this lab is just a way for us to show it, to see it, to actually do something, and, you know, do some kind of little experiment and actually measure Newton's third law in action. Okay. Another example of Newton's third law is if I push on this wall right here, the wall pushes back at me with the same exact force that I pushed on the wall with. That's the reason that the wall doesn't move, right? If there was no force pushing back from this wall, then that means it was like floating in space or something. Even then it's pushing back, but I'm accelerating it then at that point. Let's not get into the space stuff, but it just means if this wall wasn't pushing back, that I'd be pushing the wall, right? Or I'd be pushing through the wall or something. So it's got to be pushing back. It's the only reason it doesn't move. We have to have some kind of force canceling the force applied so that an object doesn't move as we expect. Okay, so that's what's happening in this lab anyway. So that's what we're going to see for the force graphs. The acceleration graphs won't be the same. You'll see the acceleration graphs will look a little different. You'll see a cell there means acceleration. Okay, hopefully it's okay. And time, and you'll see a very similar plot, except if they have the same mass, if the two carts have the same mass, let's see, carts have same mass, you'll see something like crap, what was this? 1, 2, and almost 3. Okay, that's what you'll see for the acceleration as well. That's because the thing is, we know that from last time, force equals ma, right? So if they have the same mass and the same force is applied, they'll have the same acceleration, right? Okay. And that's between the two carts. So if each cart has the same m and each cart has the same f, each cart will have the same a. Carts with different mass, the mass of A is greater than the mass of B. What should we expect? Let's go ahead and see that now. That's terrible. Okay. If the mass of cart A is way larger than the mass of cart B, then it's kind of like a fly hitting the window of a truck. This is an exaggerated example. The fly experiences an insane amount of acceleration. The truck experiences almost nothing, right? So if the mass of cart A is larger than the mass of cart B, then if A looks like this, B will look more like that. Not a very oh god. Okay, so that's what we would expect. Of course, this being A and dotted being B. We would expect B's acceleration to be much more dramatic than A's acceleration in the event that the mass of cart A is more than the mass of cart B. Okay. So that's explaining another one of the plots that you'll see. Now, so this is just basic stuff here, basically just going to go over equal and opposite forces. Then different forces would cause different accelerations. The same force would cause different accelerations if the masses are different. Okay, so that's just kind of going over some of the concepts in the actual lab here. It's too bad I didn't get to actually do this lab and see it in action. It's kind of hard to get good data sometimes in this lab, so I guess maybe that's the upside. One last thing I want to talk about is I just lost my train of thought. Oh Lord. Very important. Okay. There's a concept in physics. I think I mentioned this already, but you always want to do this. Every single time you see a plot, any kind of graph of anything, you got to check. Well, actually, I already told you the slope thing, right? So you always want to check what values your slope has. Okay. The other thing you want to do is you want to check what value an area has of the graph. Okay. So a plot, check out what units area has, okay, on the plot. And by area, I mean, you know, like a square area. So like if you're looking at, you know, an area of on a plot, you're looking at like a two-dimensional zone, right? So given a plot, check out what the what units area has on that plot. That's the first thing one of the first things you want to do. Okay, so for us, when we have well, okay, so our force over time thing isn't going to be quite as obvious. Okay, well, anyway, start with the more obvious one, I suppose. Oh, I don't know. Let's see. Force and distance, I guess. Okay. So, example. If I'm given some plot that is, let's see, force over distance. Okay, and I have some plot that's like, I don't really care what it looks like actually, so it just goes up like so. And it settles back down to zero, whatever it might be. Who cares what it is, right? The thing I want to point out here is you're given some random plot like this. You want to check out what does the slope mean. Okay, so the things, so what to do. Check slope units. Check area units. Okay, the slope here, the slope of this graph would be, you know, delta x or delta y over delta x, right? Change in y over change in x, rise over run. In this case would be force over distance. Okay, that's cute. Doesn't really tell me too much, right? Let's look at area. So if I wanted like this shaded area here, right? Shaded area A. That's what I mean by area, right? Like this entire shaded area A. That would be like, well, you'd want to, you know, for an area, you have what you have your two dimensions multiplied, right? You have like your base times height, okay? Here, this area would have units of whatever your base times height is. Of course, it would be, you know, slightly different because it's rounded. I could have made it square, but it would be having units of force times distance. Now, that's important because force times distance is actually energy. This would be newtons times meters equals joules. Some of you may have seen that before, but maybe not as well. But that right there is a kind of important concept because what I'm saying is that the units of the actual area of this graph give you some other information about what's happening in the system, right? So the area, if I want to figure out, like, let's say the total amount of energy given to some object that was forced on over some distance, if I wanted the entire amount of energy put into that object, I would just have to find the area under the curve, okay? Area under the curve sounds pretty similar to the calculus concept, doesn't it? And that's essentially what we're getting at, is that, oh my gosh, okay, hold on, let me fix my handwriting here. An area under a force versus distance curve is energy. Okay, very important concept right there. If you're ever given a force over a distance plot, just know that the area under that curve there is actually going to be the amount of energy given to that system, the amount of energy given to the object that was being forced on, okay? An equally important thing that we're actually going to work with is force over time, which is not energy, but it's something else. So let's look at that right now, force versus time. So look at some plot right here. I have my force, I have my time. I'll make it just like a simple rectangle like so. This area in here, what does this area mean? What? Okay. What does this area represent, right? Area A. Well, we look at the units, right? We would have the height times the width, right? This here is in newtons. This here is in seconds, okay? Which y'all are probably not familiar with what a newton times a second is. Let's go ahead and check that out. So what the heck does the area represent? Well, it's going to be in units of newtons times seconds. Hopefully that makes sense to everybody. If there's something weird about that, let me know. But essentially you can see here that we'd have, yeah, Emily, yeah. You can see here that we have a height times a width. And so the height here is in the newtons, the width is seconds. We get newtons times seconds. A newton is a, you get it from this force equation here. Force equals mass times acceleration. So if I want to break down what a newton is, it's going to be a mass times an acceleration, right? It's going to be a kilogram times a meter per second squared, and then times seconds. Okay, so that this term here is a newton, and one of the seconds cancels, and I get a kilogram times a meter per second. That there is actually momentum, as Emily said. If you ever have to find momentum, usually it's given you as P equals mv, which is mass times velocity. That's momentum. That's mass times velocity. Okay, and that's what we have here, kilograms times meters per second. So the area is actually equal to, and it's not just a momentum, but it's a change in momentum. Okay, this force over time is actually called impulse. And impulse is your change in momentum. Okay, so this is the important concept of the lab right here. The area under a curve on a force versus time plot has units of, newtons times seconds, and newtons times seconds is actually change in momentum. So if you, for some reason, Listo, I'm not sure what you mean, Paul. But so, yeah, so okay, so the total area under that curve there is actually going to be impulse. It's going to be your change in momentum. And that's an important part of this lab, because one of the questions specifically is, what is the area under the change in momentum? Okay, okay, so that's one of the important concepts right there. And this just leads me around to like generally an important thing to do is you always want to check what the units of your slope are and what the units of your area are as soon as you're given any graph in physics. So I want you to remember that whenever you take the next physics exam for your physics class, they give you some plot to work with and they ask you some questions about it. What's the momentum? What's the energy? Whatever it might be. The first thing you need to do is make sure you know what the slope units are and what the area under the curve means. Know what those two things are, because they're going to help you answer the question. If it tells you like a force over a distance and asks you how much energy was put into the object, you need to know that that energy is the area under that curve. It's asking what the graph has to do with the change of momentum of each card. Yeah. So the area under the curves in the graph is the change of momentum of each card. Under the curve can also mean above the curve. It just means the area is formed between 0 and wherever your curve is, whether that's up or down. Okay, that's what that area means. So yeah, so Emily, it's asking, yeah. So it's just wants you to basically state what I stated here. Okay. I think that generally does it. Yeah, that's pretty much all the concepts of this lab that I really need to talk about. The important thing that you need to take away from this lab, though, the thing that I want everybody to realize is this concept right here. Figure out what the units of your area are, right? When you see a plot, figure out what the units of your area are, figure out what those two things out before you do anything else, okay? All right. That'll answer a lot. That'll get you through a lot of exam questions in the future. Now, that being said, I think I'm going to go ahead and pull up the lab now so I can answer specific questions. Let's see. Oh, I guess I'll just keep this screen share going. Come on. Okay, and check it. So when we record the accelerations and forces in the tables, do you want us to include the negative signs, or should we just record the magnitude? Just record the magnitude. I'm not too worried about it. You know, if somebody throws a negative sign in there and then other people don't, I'm not going to be too worried about that. Just be consistent. Whatever you decide to do, just be consistent. But generally speaking, yeah, if it says something like, if it already organizes it based on the cart, so it's like cart A and cart B, you don't really have to say that it's negative necessarily. It's kind of implied, sort of. But yeah, so as far as filling the table out, I guess, go ahead and do that just to read off the data, so you have it all in one place. That's one part there, and it's literally all just from these plots that you see. You'll see that actually they tell you what the location is. Location is given in X, comma Y, right? So if everybody just looks at what the hell, part B, number 1, plot B1, you can see this is location 0.9, comma 0.8, location 0.9, comma negative 0.8. The 0.9 is the time, right? The first value is the time, that's the X coordinate, and your Y coordinate is going to be the acceleration. The Y coordinate is the one that you're looking for there, okay? Just to clarify that. And that's going to be the same for each one of these. It also tells you the area under the curve on some of these. So you don't have to actually find it yourself, which obviously you wouldn't be able to from where you are. Question 2, part B. Okay. Equal masses, one cart in motion. In this case, the blue cart changed from a state of motion to a state of rest, losing all of its momentum. The red cart did the opposite, from a state of rest to a state of motion. Where did the momentum of the blue cart go? So momentum has to be conserved, right? And this I didn't really talk about conservation of momentum. I guess this lab, we don't really do it until later, but I guess this lab kind of talks about conservation of momentum. Okay, so you've heard of energy conservation. Energy conservation is something that's incredibly useful in physics, right? Whenever there's like some process that happens, energy changes forms, we use conservation energy to go ahead and find out like different aspects of the system. Thing is that energy is often not conserved, and momentum is almost always conserved. It's always conserved. So conservation momentum can be incredibly useful just because of that. So let's say here, energy is not always conserved. What does that mean? It means that the momentum is never destroyed, right? It just changes forms. It moves into something else, or it leaves the system, but it never gets destroyed, right? So momentum So momentum is never destroyed or created, for that matter. It just moves from one object to another, essentially. Okay. Um, in a closed system, there can never be any addition or subtraction to the momentum of that entire system. The Earth Moon is a perfect example of that. If you look at the entire Earth and Moon system together, it's always going to have the same momentum, angular momentum of it spinning and the angular momentum of the Moon rotating around the Earth and so on and so forth. It's always going to be conserved unless some other object comes in, like an asteroid or something, and slams into us and slows us down a little bit. That'll change our momentum. But otherwise, the closed system does not experience change of momentum. Okay. So it's never really destroyed. It's just moved from one object to another. Now, what I'm saying here is, for part B, number 2, in the questions, where did the momentum of the blue cart go? Well, the blue cart was going, right? And then what essentially was happening in this part is that the red cart's staying still. The blue cart is traveling. It hits the red cart, and then the blue cart that was traveling forward stops, and the red cart just continues to go. So they basically traded momentum, right? The blue cart had all momentum, and it going. Okay, so that's number 2 in part B. Where'd the momentum of the blue cart go? It went into the red cart during that interaction. You can see the area under the curve for part B is the same for the A and the B cart. For the red and blue cart. Area under the curve is the same. You can see that the the blue loses 0.048 and the red gains 0.048. That's the areas there. Okay. That's conservation of momentum in a nutshell, though. As far as showing you how to actually do some problems, I don't know if that's, I think it's outside the scope of this lab now. It used to be something I talk about, but yeah. Okay, number 2, part A. What does the area under the force versus time graph have to do with the change of momentum of each cart? Yeah, it's kind of weird wording, I suppose. So what is the area under the force versus time graph? Go ahead and you can say that to me in group chat or whatever, just to keep you awake and involved here. What is that force versus time area? It's momentum, right? Exactly. So, quite like, I know it's weird. It's weirdly worded because it seems too obvious, and it is that obvious. They just want you to know. They just want to make sure that you know that, so you write it down so that you know it, right? You basically just told me that you know it already. So, what does the area under the force versus time graph have to do with the change in momentum of each cart? They are the same thing. That's all it wants to know. Do the carts experience equal and opposite forces? What about their accelerations? So equal masses, 2 carts in motion. Yes, they experience equal and opposite forces, right? And also their accelerations were the same because they were the same mass. If you looked at the acceleration chart, you'll see that they go up and down the same amount. Part B, number 1, did the carts experience equal and opposite forces? What about their accelerations? Equal masses, 1 cart. Well, yeah, so they experience equal and opposite forces. Again, that shouldn't change. Their accelerations were the same because their masses were the same, right? We talked about B, number 2, a little bit, and then part C, did the cars experience equal and opposite forces? Yes, right? The fly and the truck, when the fly hits the truck's windshield, the fly and the truck experience the same amount of force. But that force only accelerates the truck a tiny little bit because it's a huge mass, right? You have a little F, and you have a huge M, you're going to get a little A, right? But the fly has a tiny little mass, experiences a tiny little force, but that mass is so tiny that acceleration has to be huge in order to cancel it out, basically, to balance it out. So the fly experiences a huge acceleration. Off topic. How many labs do we have in total? It should be 10. I think I had it at 11, but I'm going to give you 10. Okay. As long as nothing else, as long as everything works out, that should be what we end up with. Um, okay, unequal masses. The accelerations are not equal, right? Go look at the plot and check that out. Compute the ratio of the maximum accelerations experienced by the red card versus the blue card. So that just means divide the two, right? Divide the acceleration experienced by one with the acceleration experienced by the other one. How's the ratio? Yeah. So how is that similar to their masses? I'll go ahead and let you guys look at that for a second. I'll be right back. Okay, so I'm looking at the chat here. I'm wondering how many of these questions got answered. It looks like you found out where the masses were. Yeah, there's 250 grams, 250 grams is what the mass of the carts are. Yeah, in the procedure you'll see, I think, I forget what exactly they add to it. Let's look at it. But, okay. For question 2, A and B, at the end of the lab, you just write down that F1 equals F2 over 5. Question 2, A and B. Question 2, A and B, I'm confused. So you mean part C, question 2? The ratio of maximum acceleration exponentially. You must mean part C, question 2. Or am I missing something? Oh, right. I forgot about this last page here. Okay. Yeah, I completely forgot about those questions there. Okay. So the whole Earth Moon system there at the top. Okay, so just to clarify something, number one, Earth Moon system held in orbits by gravitational force. You have some object here called Earth, smaller object here called Moon. The thing is that they're being pulled on with this F sub G, we can call it, which is some gravitational constant, mass 1, mass 2, radius squared. That force is actually experienced by both the Earth and the Moon. There cannot be a greater force on one than the other, because they're basically just pulling on each other, right? So it's like a tug of war. It's like if I'm pulling on a rope and someone's pulling on the other side, we're both experiencing the same amount of force. So that's just another example of that. So number 2 here, cart 1 has a mass of 100 grams and collides with cart 2, which has a mass of 500 grams. Right at the force exerted on cart 1, F1, in terms of the force exerted on cart 2, F2. So yeah, so thing is, the thing we saw in part C of this lab was that if you have one cart with a different mass, they're still going to experience the same amount of force, right? When they slam into each other, you can have some little cart here, and you can have some big old cart. The same force, okay? That's like the fly in the truck windshield thing I was talking about. So if I have like some, big old truck. Okay, let's just pretend that I can draw a truck. I'm just gonna turn into an art class very quick. Okay, truck and then a little fly, right? When that fly and the truck collide, they actually experience the same amount of force, right? So they both experience a force F, and then for the fly, it has like mass F, right? Massive fly, and then truck has massive truck. Thing is, that little force there is equal to the mass of the fly times the acceleration of the fly. That little force that we experience is also equal to the mass of the truck times the acceleration of the truck, right? So they're equal to each other. Mass of the fly, acceleration of the fly is equal to mass of the truck, acceleration of the truck. Those things have to be equal, and we know already that mass of the fly is much, much, much smaller than mass of the truck, right? That must then mean that the acceleration of the fly is much, much larger than the acceleration of the truck. Little m and huge A equals big M and little a. It's basically saying like 3 times 4 equals 4 times 3, right? The only way that those two things can be balanced is if one's small and the other one's large, and then it alternates, right? Hold on one second. So, yes, at the end of the lab here, and so this whole idea here is the fact that this all starts with my essential assumption here that the fly and the truck both experience the same amount of force. And I'm explaining a way that makes sense because I'm trying to show you that because of the mass differences, the fly experiences an insane amount of acceleration from the same amount of force. Okay, so the fly, as you expect, it was going one way, then suddenly accelerates to be going the other way, like 60 miles an hour instantly. So it has, way bigger acceleration. The truck doesn't feel anything measurable. So there you go. So that just A here. The fly and the truck experience the same force, therefore the cart 1 and 2 experience the same force. The acceleration of cart 1 in terms of acceleration of cart 2. So yeah, so that's when you would go ahead and just, okay, so they experience the same force, so when they collide, little cart and then big cart experience the same force from the collision. Mass is, I'll call it mass 1, cart 2, mass 2. They'll experience F. So this thing's, second law equation, F equals ma, is going to be F equals m1 a1, right? Cart 2 is going to be the same F, but equals m2 a2. And what do we know? We know that one's 500, the other one's 100. So we know that, we know that m2, well, hold on, let's just go ahead. So, okay, both these F's equal each other, so we can set these equations equal. So m1 a1 equals m2 a2. And then I'm going to go ahead and say, well, what do we know? We know that mass of 2 is equal to 5 times the mass of 1, right? And so go ahead and substitute that in there. So let's see, I can say that m1 a1 is equal to 5 m1 a2. And what they want is they want to write a1 in terms of a2. I can go ahead and divide each side by m1 here. And I'm left with a1 is equal to 5a2. That would be the proper way to derive that. But there you go. That's the solution. So we have, F1 is equal to F2. And they're actually here both equal to F. And then that gives us that A1 is equal to 5A2. Like I said, when this lab was in person, I would actually I'd run around the room. I couldn't help everybody at the same time unless there was something I noticed everybody was doing wrong or whatever, then I would do it in front of class. But I would just run around the room and help everybody. And, as long as you were there, I would just help you through the problem. So that's why I'll give you guys a moment, and then I'll just do these with you, because I'm not too worried about like testing you on this. I just wanted to make sure you're paying attention to it. You know, again, I know I keep saying that, but I don't know. I guess that's my philosophy. Okay. Hopefully everything else got figured out. Some questions up here. I saw some back and forth. Just if anybody's still confused, just say anything in the group chat. Okay, for number one in the summary, when accelerations are not equal in part C, it implies the carts have different masses. Is that sufficient? And summary section. So for number one in the summary section, essentially you would just have to say, do the masses always experience equal and opposite accelerations? And your answer is no, right? Because the unequal mass section. And then the other short answer would be, when are they not equal? You'd say when the masses are not equal. What you said is true. The accelerations are not equal in Poisson, right? Yeah, I mean that really, I would agree that as 100%. You could just throw in also a no, just a short answer, the short answer question, or a short answer to a short question. Do the masses always experience equal and opposite accelerations? And they don't, right? There's just that one situation where they don't. So you just say no, and then you would say what you said. They're not equal when they have different masses. Part C, question 3. Part C, question 3. Would be the same ratio of 1/2 for the masses. Well, let's find out. Let's find out, Chris. Let's check it out. So, what do we got here? We have that. How does the ratio of the accelerations of the carts compare to the ratio of their masses? So, let's say that acceleration from 1 is twice acceleration from 2, right? So let's set up this relationship and see how the force works. We know that the forces are going to be the same. F1 is going to be equal to F2, right? Because of this whole Newton's third law thing here. So we know that F is going to equal M1A1, and we know that F is going to equal M2A2. Right, so that's just for each individual cart. We know that the force is going to equal MA, and the force is going to equal MA for each cart, right? So when the forces are equal to each other, so we set up these independent Newton's second law, F equals MA expressions here, and they're equal to each other. So I can say that M1A1 is equal to M2A2. I'm going to go ahead and substitute in that relationship of A1 is equal to 2A2. So I have M1 times 2A2 is equal to M2 A2. Oh, did I do something stupid on this last page here? No, okay. Okay, so I can go ahead and divide out the A2, so I'll get that 2M1 is equal to M2. So look at that. So I started with A1 is equal to 2A2, and I got that 2M1 is equal to M2. So what they want is ratio of the maximum acceleration experienced by the red cart versus the blue cart. Okay, so let's say that 1 is red and 2 is blue. Okay, just for argument's sake, what would that imply? The ratio of the maximum accelerations. So that would be the red cart versus blue cart. So they want red to blue ratio. So I guess I'll do like, so that would be A1 over A2, which would be A1. Wait a minute. It would be 2A1. So, oops. It would be 2A2 over A2, which would be 2. And then if I wanted to do M1 over M2, mass is the same ratio, but except for masses, I would see, what do I have? I have 2M1 is equal to M2. Okay, so I keep the top M1 and the bottom, I get a 2M1, and I would have a ratio of 1/2. So you can see here that in the case of, 1 being red and 2 being blue, and it doesn't really matter which one they are, that the ratios are actually inverses of each other, right? So it's the power -1. So whatever A1 to A2 is, the power -1 of that is whatever M1 over M2 is. Oops, it's running out of room here. Okay, that doesn't really work. They're inverses, though, is what I'm trying to say. But that's how we check, okay? Chris, I just want to make sure that I just want to show people this, and so they can look through it and kind of make sense of that, because this is what I want people to take away from this lab here. It's just this kind of stuff. That's why I like making sure I show you guys this. Yeah, I don't know where to write this, but damn it, how do I? Peach, say hi. Say hi, Peach. Bye, Peach. Yeah, I wanted to write this because it would be cool and kind of fancy, but I can't. I can't put it anywhere. Yeah, there you go. The inverse, so that the power of -1, so the reciprocal, I guess another way to say it, of the ratio of A1 to A2 is what M1 to M2 ratio is. Anyway, being fancy. So is that it? Let's see. That part, and okay. And then answer number 1 in the summary section. Hopefully that made sense, whatever I said. I forget what I said, but I know I said something. Right. Yeah. Your answer, yeah. Okay. Yeah. Everybody said no. Peach. Oh. Okay. So computer just died, which is kind of strange. It told me I had a full battery, and then it just told me I was dying. And I ran to grab my cord and died before I could even do that. So it's a little lame. Nevertheless, I'm still here. I'm just unable to be. I can't record right now. Um, okay. Let's see. Um, hopefully the interpreters can hear me right now and that you're doing that because I can't see you guys and I can't really type too easily on this thing. Data table 1, table 2, the blue card's maximum is going to be. I see you're saying okay. No, just pretend it's the absolute value, right? So just make it positive. So maximum, and yeah, you're correct. I mean, the largest positive value is 0 for the blue, right? And then, but just treat it like an absolute value. For number 2 in the summary, it's the same as number 1. Okay, sorry. Let me just pull this up again. It's really unfortunate that it did that. Yeah, just absolute value. Yes. Yes. Okay. Let's see. Number 2 in the summary is 1, right? Okay, pulling it up now. Summary number 2. Compare the maximum forces recorded in each part of the experiment. Do the masses always experience equal and opposite forces? Well, you tell me. Do they experience equal and opposite forces? And if you look at all the force plots, you'll see that that's true, right? A and B always experience the same force, just opposite directions. So like one goes down, one goes up, but they're the same. Okay. Oops. Okay. I think we're good now. Okay. We have to turn you down all the way. Mute you. Fine. All right. Good. All right. Severe technical difficulties here. Huh. Well, that really sucks. Looks like I may have lost the recording, I guess, which is really just oof. Oh yeah, I tell you what.